Alright, what are we doing today? Some math or what? Alright, here we go. We are live. This is question number 3, section 8.3 on confidence intervals for a single population mean. That is estimating a population mean. Alright, let's go for it here. In the problem it says industrial chemicals may enter the body through pollution or as ingredients in consumer products. In October 2008, the scientists at HTP Human Toxome Project tested cord blood samples for 20 newborn infants in the United States. The cord blood of the in utero newborn group was tested for 430 industrial compound pollutants and other chemicals. Use the sample data to construct a 90% confidence interval for the mean number of targeted industrial chemicals found in an infant's blood. Assume that the toxicity level of the blood are normally distributed. Okay, you can see here, like the other problem that we did, we have a data set that needs to be entered into some sort of statistical calculator to find the mean, variance, standard deviation, more specifically just the sample size, sample mean, and sample standard deviation. So I've already set that up here on using our calculator, more specifically calculator.net. I have that link in modules. I've entered in those values here. Go ahead and calculate that. I think it's already generated those values. You can see here the sample size goes with a count. It is a sample size of 20. The mean, the sample mean, is 127.45 even. And down here towards the bottom for the sample standard deviation, the 25.9645 0.00055,998. But of course, we'll be rounding that to a specific number of places looked at over here on the screen. Since these are whole numbers, we want our answer to be one more place than that. So therefore, all intermediate values need to be double 1, which is 2 places. To go back over those rules of rounding, sort of like I've emphasized before, going back here to section 2.1, there it is there. Again, reading this off, it says a simple way to round off your answer is to carry your final answer one more place than was present in the original data set. So again here, because those are whole numbers, we want our answer to be one more place. Round off the final answer. Do not round any intermediate results if possible. But if it becomes necessary to round off intermediate results, carry them at least twice as many decimal places the final answer, and that's why over here those are all repeating decimals. I went twice as many as the final answer, and that is why I came up with 2 places for those. So with that, going back over those rules stated in section 2.1 of the book, we'll come over here to part B. It says verify the requirements needed for the confidence interval. That is, the sample size is greater than or equal to 30, or X is normally distributed. So, of course, here with the sample size, that is less than 30, so we have to know. And looking at that last sentence here, it says that the toxicity levels in the blood are normally distributed. So we're okay there. We can go ahead and use the student T distribution, which goes along with parallels with the concept of finding the population mean. So now I can jump over here on GeoGebra and bring up the student T calculator. For short there, just says student. That was Gauss's pin number. Alright, for part D, finding those critical values, the lower critical value and upper one. Since in the problem, going back here to the top, says use the sample data to construct a 90% confidence interval for the mean. That is for the population mean. So what we want to do, as I stated here, we have that level, 90%, middle 90%. In decimal form is 0.90. You want to take the complement of that and divide by 2. So again, grabbing a calculator, a little simple calculator here. You can pretty much do that stuff in your head as well. It's decimal form, let me go back here, 1 minus 0.90. Of course, is 10% divided by 2. And that is what we'll be putting into GeoGebra. You can already see here on the right side here, I've already got in that 0.05 in the bottom right box. And of course, the degrees of freedom is the sample size minus 1, and that's what I have here for DF. So 20 minus 1 will end up using 19, and there it is there for the 19. Alright, so here for using the left bracket, you get negative 1.7291, and there's your lower critical value. All you need to do is drop that, change the sign, opposite sign, because for using a symmetric distribution, you easily come up with positive 1.7291, but if you want to use either bracket to do that, you just have to toggle back over here, changing the bracket to the right, and then placing back in the complement divided by 2. And there is positive 1.7291. There's the upper critical value. Right, use that number to calculate the margin of error. And the margin of error only applies to a symmetric distribution. I'm trying to highlight that here. So there it is there, 1.7291 times the sample standard deviation. Again, up here at the top, that's what we did using the statistical calculator there, the 25.96. And divided by the square root of the sample size there, get the 10.04 toxicity level. Like I did the other problem. On this calculator on my computer, I have to do this backwards. 25.96 divided by 20, but square root that, then equals, and then last multiply that times the critical value, 1.7291, and there you go. Again, it's those two places to the right. If you have a graphing calculator, you can simply go from left to right. Okay, now taking that number, that's your margin of error, you want to subtract that from the point estimate. This is the middle value here, the sample mean. So the sample mean is the point estimate because we want to estimate there it is there, for a population mean. So take your point estimate, subtract the margin of error, add the margin of error, you get the two levels there for toxicity. And then we can finally conclude here at the bottom, using that level of confidence, that the population mean, or mu, is between 117.4 and 137.5 toxicity level in newborn babies. That'll complete it for problem number 3, section 8.3, estimating a population mean.